Well, first of all, thank you very much for the introduction. I must admit, I'm not going to use the microphone, so I hope you can hear me, okay? And if you can't, it's okay to raise your hand and tell me you can hear very well. And I hope to a certain degree that that happens, because that means that you're paying attention and you want to listen to me, all right? So I must confess I couldn't understand most of what was said because I don't speak German. And it was probably a great thing, because I don't like to listen to others talk about me, good or bad. Okay, so, but thank you very much for your words, and to both of you, and it is an honor to be here at the University of Innsbruck. This is a special place for me, not only because of my relationship with Professor Adam, but also because my mentor and my PhD advisor, Professor Helmut Krauwinkler, was from Innsbruck. The late Helmut Krauwinkler was born here, and it is really an honor to be here at the University of Innsbruck and in his birthplace. So with that, I am going to start. If you look at the title, Protecting Lives and the Built Environment Through Research in Earthquake Engineering, that to a certain degree is promising a lot, because what we're saying is that we are doing research in earthquake engineering, and by doing so, we're also protecting human lives and the environment. But that relationship between research and protection of human lives is not that straightforward. Why? Because we cannot do research for the sake of doing research. Okay? It's good for us professors to write journal papers. We get promoted the more papers we write, and we go to conferences. But the ultimate goal, in my mind, is to have at least some of those results influence practice, because this is ultimately what we do research. So research has to transfer into practice, and then practicing engineers have to communicate to the general public what the intent of the seismic design provisions are. So I will talk a little bit more detail about this as we go along today, but one point I want to stress is research has to find its way somehow into practice for this title to actually become a reality. So now we're talking about earthquake engineering. Let's define it, and you will see why in a few minutes. Earthquake engineering is a scientific field, so there is science behind it. Okay? But it's concerned about protection, earthquake protection, rather than earthquake prediction. You'll be amazed throughout my life and my career. I have met people, and when they learn that I do research in earthquakes, they think that I'm working on predicting earthquakes. That's not what earthquake engineering is all about. It's about protecting lives, it's about protecting the built environment and the natural environment also. Now, how is that accomplished? Well, by limiting seismic risk to an acceptable level. And when we talked about risk, that has to do with social, economic, environmental risks. Now, the key word here is risks, limiting risk to an acceptable level. What is an acceptable risk? This term is a little bit ill-defined, because this is not something that engineers or researchers can actually define. Those levels of acceptable risk have to be defined by society. And we will touch upon that a little bit later today. So talking about this whole issue of protecting against earthquake versus predicting earthquakes, I want to spend a couple of minutes addressing a very timely issue. A couple of years ago, 6 Italian scientists, after the L'Aquila earthquake, they were convicted with manslaughter charges because they failed to predict that an earthquake, the L'Aquila earthquake, was coming after a series of tremors affected the area. Luckily, as of November 10 of this year, those charges were cleared. Now, that's not the end of it, because apparently prosecutors are going to go and appeal, or may appeal, to the Supreme Court. But the issue is that the general public was upset with the scientists, one of them a professor, a university professor, a researcher, because they failed to predict this earthquake. So now, right there, we see there is a communication gap. there is a misunderstanding between society, the engineering community, and the research community in terms of what we're able to deliver right now when we say that we're working on earthquake engineering, earthquake-resistant design, and earthquake protection. Okay. So now, I have been talking about earthquake engineering. So obviously, those who work in earthquake engineering are so-called earthquake engineers. However, especially students, you see, you don't get a degree, you don't get a master's degree, or you don't get a doctoral degree in earthquake engineering per se in most places. You get a degree in civil engineering, civil and environmental engineering. So the question is, what is an earthquake engineer? So I'm going to start, one of the most closely related disciplines is civil engineering. So what does a civil engineer do? What does she or he do? Well, a civil engineer is one who designs, constructs, supervises, operates, and maintains large construction projects. But there are various fields within civil engineering. One of them is structural engineering. The structural engineer actually designs and analyzes structures, bridges, buildings. But there are also fields such as geotechnical engineering, where the geotechnical engineer has to deal with earth materials, how they behave, substructures. When you think of protecting against earthquakes, you have a superstructure, you have a foundation, soil that interact during the ground shaking. And there are other fields. Transportation engineers may claim to be also earthquake engineers. They deal with bridges to a certain degree. We have a traffic network. Okay? So my point is that by studying civil engineering, you can specialize on fields such as structures or geotechnical engineering and become what is called an earthquake engineer and work on earthquake protection. So now you have this guy in front of you. So what am I? Or who am I? That doesn't sound. I actually specialize in structural engineering. Yet I consider myself, and some consider me an earthquake engineer because I did research as a master's student, as a PhD student, as a faculty member, and as a practitioner. Because one of the things that I'm very proud of, and on the first slide it shows, you see my name, and then you see PhD, and then PE, a professional engineer. I'm a licensed professional engineer in the state of New Hampshire. Okay? I interact with practitioners, and I'll share some of those experiences with you later today. Now, going back to the overall issue of earthquake protection. Obviously, as engineers, our number one goal is public safety, life safety, and collapse prevention. Every single building code out there, in the world has as a performance target, a basic performance target, life safety and collapse prevention. Now, I took this particular plot from a study done by the University of Colorado, and it shows on the horizontal axis, here you see the magnitude of the earthquake. That's some measure of the intensity, how intense it is. We know as engineers and researchers, it is not the best way of characterizing an earthquake. But generally, when you see in the news that there is an earthquake, one of the first things that is reported is the magnitude. Okay? So now we're taking the intensity here. Pay attention to the vertical scale. It's actually a logarithmic scale. That's the number of casualties as a function of magnitude on a variety of events throughout the world. Unfortunately, what you see is that in countries where maybe design codes are not as developed, or they are, but building and construction practices are not up to par with the design codes, is where you see most of the casualties. Okay? So these are non-successes. What we want is to be right here at the bottom. Okay? That is the ideal, 0 casualties. However, that's very difficult to achieve, but there is a lot of smart people doing research and working towards that goal. Now, I pointed out a couple of green circles here because these are the 2 Christchurch, New Zealand earthquakes, and I'll talk a little bit more about them in a few minutes. Okay? The first earthquake was a magnitude 7, no casualties. The second earthquake, Following year was a magnitude 6.3. And there were 182 casualties approximately. And why? Because 2 buildings collapsed. Okay? But our number one goal is to make sure that we are down here when it comes to casualties. But that's not the whole story. Losses are also important to an earthquake engineer. We want to minimize losses. This chart gives you, a study, the results of a study on leading natural disasters by overall economic losses. If you know something about earthquake engineering, tectonics, and seismology, you will see that these are the regions where most of the earthquakes occur. Right? Now, in some of these, you actually see, every time you see that circle, that's an earthquake, 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 earthquake. This one was followed by a tsunami. But still, you see earthquakes leading in terms of natural disaster causing significant economic loss. And these numbers here are in the billions of dollars, 89 billion, 40 billions, 148 billions of dollars of losses. So even though the basic performance target in building code is life safety and collapse prevention, society demands more from us because we need to also contribute to limiting these losses. Fortunately, there is a framework, an established framework called performance-based engineering. During the last 20 years or so, it has developed all over the world, and it gives us a means to actually get to that objective of mitigating losses, collapse, and casualties. I'm going to show you now a definition of performance-based engineering and give you a few seconds to look at it. Does anybody know who wrote that quote by any chance? You know, who said that? Absolutely. You're absolutely right, as he would say. Professor Helmut Krauwinkler. That was close to 20 years ago. And he was one of the visionaries that worked at the Pacific Earthquake Engineering Research Center in California when I was a graduate student and started this whole notion of performance-based engineering. And I want to highlight this. We want engineering facilities whose performance under common and extreme loads, earthquakes are considered extreme loads, responds to the diverse needs and objectives of owner, users, and society. Now, let's think about it. Performance that responds to the diverse needs of society. That's a tall task. And not only that, that requires that we're able to predict performance and evaluate it with confidence when there is so much uncertainty. Okay? But that is the vision, that is the framework. But what we're going to deliver to society, or what we will promise society, is very difficult to achieve. Yet through research and by actually having researchers communicate with practitioners and implementing some of these design concepts, I think this is a goal that we can achieve, and we're on the right path toward that goal, as you will see during this presentation. So just to stress that point, now we're not only talking about collapse, life safety. We have an example of a building right here that survived the earthquake. Nobody died inside the building. The basic performance target from the building code is life safety and collapse prevention. That was a success from that point of view. Yet you see a sign here that says danger, no entry. Owners are not very happy when they see something like this. She doesn't look very happy. Okay? So as engineers, we have to think about, okay, we want to do performance-based engineering, but what are the consequences of that, and what can we really promise or deliver to society? So Let's talk about the example of the Christchurch earthquake, or the series of events. The first event was a magnitude 7, as I told you earlier. No casualties, yet $3 billion in losses. The second earthquake, 6.3, $16 billion in damages, 182 casualties. But what I want to stress is this bullet point here. Downtown and the central business district is still being rebuilt. Nobody wanted to own anymore in the central business district. People fought for insurance payouts and demolition of structures. Over 1,000 buildings had to be demolished. Now, these are buildings that didn't collapse. But sometimes it's cheaper to demolish a building and reconstruct than to try to fix it. So this is what I mean when I say that society demands more from us, and there's a great opportunity for researchers to do something about it and implement some of those results into practice. Another point I want to stress is 2 buildings collapsed. Now, in the United States, we designed for what is called the maximum considered earthquake. You go to a hazard map, you pick a value, you use that value to estimate seismic forces, size members, design a facility for that. But what most people don't know, and part of the reason is that there is a failure in communication, is that if an MCE, a maximum considered earthquake ground motion, were to affect a site at any given time, the target performance is a 10% probability of collapse. Now, in Christchurch, 2 buildings out of many collapsed. That's way under the 10%. And the ground motions experienced at Christchurch were design-level events. They were MCE-level ground motions. Okay? From that point of view, that was, if you apply US standards, that was a success. However, one cannot talk about a success really when there is at least 1 human life lost. On another note, the public was upset with engineers who green tagged the 2 buildings that collapsed. Let me explain that a little bit more. After the 7.0 magnitude event, and this happens all over the world, there is a group of engineers who go to facilities, they inspect the facilities, and then they put a green tag, a yellow tag, or a red tag. After this one, the first event, the 2 buildings that collapsed were green tag, meaning that people could go back and occupy the building. There was no imminent collapse danger. So part of the communication issue that I'm talking about, or that I would like to stress also, is the fact that green tagging a building doesn't mean that the building will be safe under a future event. And there was a big misunderstanding after that particular series of events, which stresses the point again of communication. What is it that we want to deliver to society, and making sure that society understands what the performance targets are? Just to give you a little bit of an idea of what these tags look like, I took this from one of my friends, John Silva, who visited Napa Valley after the August earthquake in Napa, or near Napa, California. And these are typical, you know what I will do? Give me 1 second here. Is that better? Okay, this is a typical red tag. So engineers go in and then they put it, do not enter or occupy. However, it's not a demolition order. Okay? Now, likewise, yellow tags can be placed on buildings. This is for restricted use. Maybe there are portions of the facility that can be used, some portions shouldn't be used. Or you can have a green tag, which means that based on the assessment of engineers, the building can be reoccupied. Okay? Now in Christchurch, 45% of the buildings in the central business district were either yellow tag or red tag. Think about it, 45% of the buildings, either yellow tag or red tag. So we can do better as engineer professionals, and we should do better. This is just a picture of one of the buildings that collapsed in Christchurch. 18 people perished on this particular facility. Now, this is another example of two tall structures. Now, this picture was taken right after the event. So you see the buildings look intact, right? This one had a permanent deformation of 25 centimeters at the roof. The other one had a permanent deformation of 46 centimeters. The question is that acceptable? You know, this building survived the event. Life safety was preserved, collapse was preserved, but they have to be demolished. So, within the framework of performance-based engineering, what is it that we need? We need a probabilistic framework, not a deterministic one, because of all the uncertainty, not only on ground motion, but also the uncertainty on buildings, on our ability to predict performance, not only behavior, but performance. Now, we also need a framework that addresses consequences of building response to events in terms of casualties, direct economic losses, indirect economic and social losses, and environmental impacts. More specifically, for this to become a reality, we need performance measures. And this is part of what the peer center that I previously mentioned developed as part of a methodology, the 3Ds. We want to establish performance based on direct dollar losses, downtime, and deaths. Okay? It's no longer enough, and it will not be enough just to work on life safety and collapse prevention. So what are the challenges? What are the needs? Well, we need a reliable quantification of behavior and performance. But if we want this to become a reality, we not only need to focus on earthquakes, because that's not the only type of hazard. We have tornadoes, we have high wind hazards, we have fires. If you talk to insurance companies, their number one hazard is fire when it comes to protecting buildings in general. Now we need to be able to estimate, quantify losses, and not only losses, but consequences. We need to treat uncertainties. We need to develop transparent, performance-based design methodologies. And communication and collaboration are key issues. Communication between researchers, practitioners, and communication with the general public. Now, there are a lot of challenges when it comes to this communication, and I want to address that in the next couple of minutes. Through my experience as an academic and also as a member of many professional committees involved with writing load standards for seismic design, I have run into different points of view. I would call them extremes, okay? And everything in between. What I'm about to show you, I didn't make up. These are things that I've heard. Well, we talked about the communication between research and practice. We have our good old friend, the engineer here, looking at the researcher or the professor. Okay. Well, they don't live in the real world. They stand on their ivory towers. They're probably teaching because they cannot handle the real world. They have all the time in the world, and they produce very little that is actually useful. And they even get summers off. And they travel all over the world going to conferences. They have a great life. I'm not making this up. These are things that I've heard. And these hinder the ability to work together. But again, that's an extreme view. On the other hand, you have the professor. I almost took a picture of Professor Adam there, but I didn't dare to do it. I was going to put myself, but I said no, because he doesn't agree with these things. So I didn't want to give the wrong impression. Looking at the engineer, and then thinking, well, nice ladies, nice gentlemen. They need some education on state-of-the-art stuff. Because, we do state-of-the-art, but they don't. Our theories and our methods need to be simplified so they can understand them, because they're never going to understand what I wrote in my paper. and they tend to think only about the bottom line, costs. These are two extreme views, and I have experienced these extremes at anything in between, everything else in between. But fortunately, there is a framework, and that has been my experience in the United States, which formed the basis for this talk and for sharing these thoughts with you. There is a framework in place where researchers collaborate with engineers. Okay? And it all starts with the development of NEHRP, National Earthquake Hazard Reduction Program, recommended seismic provisions. I capitalize researchers here on purpose because these groups are made primarily or composed primarily of researchers, professors, and you also have practitioners. These provisions are put together based on state-of-the-art research, but they're not regulatory. Then these are taken by committees from a committee, ASCE 7, from the American Society of Civil Engineers. I'm a member of that committee. Most of the members are practitioners, and then you have some researchers. Okay? We have the task of adopting a lot of these seismic provisions. And we actually have to justify if we don't adopt a specific change that is recommended. Okay? So there is a lot of work here, but this is not regulatory either, because then the ASCE 7 document is taken by a group here of primarily building officials and practitioners, and who are the ones who develop the International Building Code. Okay? So research gets into practice, and there is an established framework. There are a lot of challenges. Not everything is as straightforward as just showing a few red arrows here, but at least the framework is in place, and we need to debunk some of the myths and stereotypes and actually also work on improving lines of communication, but we're getting there. Research results are getting into building codes, but there's much more that we need to do. So far, I have tried to set the stage for what I perceive as the main challenges in terms of having research influencing practice and ends working towards the protection of lives, the built and the natural environment. And what I'm about to do right now is share with you a little bit of what I do to contribute to this framework, or to this problem, to solving this problem. The first thing I want to say is there are many research needs, many of them, but I am going to focus on two of them. And the first one is research needs on protecting what is called non-structural components and contents. An example here, you see a suspended ceiling that collapsed after an earthquake. Think about this suspended ceiling on a school or a hospital. I mean, it's not enough to provide life safety and collapse prevention. There are certain buildings for which you want to maintain functionality during and after an event. These are the so-called essential facilities. You could also have equipment actually falling or anchors failing. Okay? So in terms of non-structural components, I put together a laundry list. I'm not going to go over every single thing that is here on this wordy slide, but it goes all the way from horizontal pumps, engine generators, to architectural components. There are many valuable assets that we actually want to protect, not only because they cost money and they're valuable, but also because they could cause injury to occupants of a facility. Now, if you run a museum, there are art pieces, there are things you want to protect. This is an example from the Napa Valley earthquake, a statue that fell, but there are also so many other valuable assets that are worth protecting. After the earthquake in Napa Valley, a lot of wine barrels actually fell, and a lot of wine was wasted. Now, we're laughing about it, there were no casualties, no building collapses, very minor damage other than to wine barrels and, in certain wineries. But the dollar losses from that Napa earthquake actually exceeded $1 billion. That's an outstanding figure for such a moderate-sized earthquake. And just to stress on that point, I'm showing a graph here developed actually by Professor Eduardo Miranda from Stanford University 9 years ago. But that still applies today. There was a case study, a building in Southern California that was selected to apply the performance-based engineering methodology when it was at its early stages. And think about having a facility and then thinking that that facility is going to be there, let's say, for 50 years. It's in a seismic area, so people identify where all the faults are, and then calculate what are all the possible earthquakes that can occur from all the faults around the area that may affect the facility. Take into account all the uncertainty and the variability, and somehow come with an estimate of an expected annual loss for this particular facility. What you see on the pie chart here on the left is that on any given year, 71% of the expected annual loss comes from non-collapses. These are damages to non-structural components, damages to contents. Okay? Only 29% come from a potential collapse of the structure. Now, if you look at the pie chart here on the right, 88% of the damages come from damages to the non-structural component and only 12% to the structural ones. So these numbers are very telling. And the question, or one of the questions is, how are we handling this right now, given that we don't have performance targets in building codes that address economic losses directly? The way this is handled nowadays in the United States is by having a force-based design when it comes to non-structural components, but there are certain problems. Why? Number one, let's see here on the left side, you see a ground motion intensity. That's just some measure of how strong the shaking is at a given site. On the right, you see descriptions of performance for components that are in regular facilities. Okay? Now, the code says that if you read the commentary, it says that a performance target is, for minor ground motion intensity, but that's not defined anywhere what minor means. For minor intensities, you want minimal damage and functionality impairment unlikely. Now, if a moderate level of ground motion hits the site, and that's not defined anywhere what moderate means either, well, some damage is expected, functionality potentially impacted. Okay? But then you see, if the design earthquake were to hit the site, then major damage of non-structural components is expected, functionality loss likely, but significant falling hazard is mitigated. Now let's think about it for a minute. The performance target of current building codes under a design earthquake on regular facilities is to have major damage on non-structural components. But what we don't want, and functionality impaired, but what we don't want is a component falling on somebody's head. Okay? So we definitely can do better, we should do better, because society demands more from the engineering community. So a long-term goal is a performance-based design approach that explicitly incorporates losses due to damages to non-structural components. This is where we're headed. There are a lot of smart people around the world doing research on this particular area. And I'll give you an example result. Towards this goal, we need to come up with what is called fragility curves. So let me go over it. On the horizontal axis here, think of that as some measure of deformation in the structure. Okay? So the higher the number, the more the structure actually deformed. And on the vertical axis, you see the probability of being at or exceeding a damaged state. Now, how do we define a damage state? This is the green one where you may have just cracking on the partition on the walls. Now, you could have the yellow type of damage state where you see that damage is more significant, or you could have an even more severe damage state. So how do you read this curve? For a given deformation, if the deformation is small, the probability of being a damage state, yellow or red, is 0, which makes sense because we will most likely have small damage. Okay? But as the deformation increases, we increase the probability of being on that particular damage state. It is not easy to develop these curves. And most likely we need these curves developed experimentally and then experimentally and numerically. Okay? But there is so much uncertainty in the process. Think about it. There are various construction practices around the world. Okay? And we cannot have a single magic set of collapse fragility curves that work for all components of its class. That's almost an impossible task to achieve. But there's a lot of research done in that area. And the other thing is, this is not the end story. This only gives you a probability of being at a damage state or exceeding it. But then there are consequence functions that relate that damage to actual dollar losses. And if we think a little bit more about it, we can easily realize that there are all sorts of challenges there. If you have walls that crack, and then you bring contractors to estimate how much it will take to repair that. If you bring 5 different contractors, you're going to have 5 different estimates. So there is uncertainty there. And another problem that we have is that we may develop these so-called fragilities for a single component. But we need to aggregate damage. If we have a multi-story building, it's not as simple as saying, well, it's going to cost me X amount to fix the partition here. I have 100 partitions or walls that need to be fixed. I do 100 times X and I get the total cost. It doesn't work that way because contractors are not going to charge the same. The rates are going to change. So there are a lot of challenges there. And a lot of things that we could do, but that's a long-term goal. A lot of people working on it. Short-term, and let me define what I mean by short-term. There are opportunities on these code development cycles that I talked to you earlier to provide supplements or, if you wish, incremental but important changes to design provisions. And this is part of what I'm working on currently. Right now, to design non-structural components, remember, we don't want things falling on people. We don't want things blocking means of egress so that people can evacuate a building after an event. So it's important to characterize and quantify the demands, force demands on attachments, compare them to capacities, because that's what design is all about. You compare capacity to demands and you make sure that the capacities exceed the demands. So when it comes to demand quantification, I am currently collaborating with Professor Adam. So there's an established collaboration between the University of New Hampshire, the University of Innsbruck, and one of his doctoral students, whose name was mentioned earlier, Lucas Motion. I told Lucas, do I have your permission to embarrass you a little bit? He said, yeah, of course. Yeah. So, and basically, what are we doing? Well, we're taking buildings of various sizes, various configurations, various lateral load resistance systems. We're placing components. That's my rendition of my cartoon of a component to the component, the support, and the attachments in blue. And then we're doing a lot of analysis to quantify the demands on the attachments. Why? Because right now, the building codes actually give you a distribution of forces. The higher up you're in the building, the more forces the building, seismic forces the building is going to attract. But there is an upper limit here that we're evaluating. My personal opinion, based on years of research, is that upper limit in the building code is too low. But as part of the ASC 7 committee and my involvement with the American Society of Civil Engineers, I need to demonstrate to them somehow and convince them that the limit is too low, too small. And that's part of the reason we're doing this analysis. And we're producing plots of this type. This plot actually produced by the student, but I can take credit for it. Why not? On the horizontal axis, you just see some characteristic of the component. Here, as you move here, the component becomes flexible. As you move to the right, then the component becomes stiffer and stiffer. Then on the vertical axis, think of the vertical axis as the magnitude of the force demands on the attachments. The red line here gives you an indication of where that upper limit is based on current seismic code provisions. Clearly, in these couple of examples, the upper limit was exceeded. Okay? So we're doing this probabilistically. We're quantifying uncertainty, looking at different models to hopefully come up with a document, not only a journal publication, which will be great for all of us, but also with a product that can be incorporated into building codes. Now, that's on the demand side, but we also have to look at the capacity. And I'm involved on the development of what is called a Chaik-Taylor certification standard. And let me explain what that is. If you're a manufacturer of equipment, a generator, the generator is going to go in a hospital in California, for example. That needs to be seismically certified. What that means is that that piece of equipment is brought to a facility that has an earthquake simulator, a big plate with actuators, and then a ground shaking is simulated on the earthquake simulator. And if the equipment at the end of the test, quote unquote, survives those motions and is functional, then you say, well, it's seismically certified. You don't need to test, a manufacturer doesn't need to test every single equipment on a line of equipment. Maybe a representative one, and then extrapolate and say, if this one survived, this other one of a similar class will also survive. So this is the capacity side of the equation. What can we learn from that test to determine capacities? And I'm also doing research on modifying this testing approach because this is the right time to do it. There is an acceptance criteria that was developed by the International Code Council around, in the late 90s. Okay? This is what most manufacturers use, but this is not a standard. So right now, as we speak, we're in the process of developing a standard for the American Society of Civil Engineers to better quantify capacities. And that's something that we can accomplish right now as a short-term goal to improve safety and minimize damages to non-structural components. Now, another set of research needs, and I'm going to go back to our main objective, which is life safety and collapse prevention, is to prevent collapse. With one of my students, one of my former master's students, we actually designed a structure, a 20-story structure in Century City, California. That's very close to Los Angeles. Okay? It's a steel moment resisting frame structure. We did a numerical model of the structure and then expose that. Don't get bogged down with the details here. This is not important. We expose them to a set of hundreds of ground motion and quantify uncertainty in our model, uncertainty due to variability in ground motion characteristics, and went through a process where we hit the structure from left to right with different type of earthquakes, and at the end of the day, estimated the probability of collapse in 50 years. That value was around 1%, which is very good. And I'll tell you why it's very good. Because the performance target in the United States for new buildings right now is to have a 1% probability of collapse in 50 years, which means that during the lifetime of that facility, when the facility is going to be exposed or could potentially be exposed to a myriad of ground motions and earthquake events, we want the probability of collapse not to exceed 1% in 50 years. Now, this was just a case study. Okay? Professor Charney at Virginia Tech has many more buildings. Some of them are below the 1%, some of them are above the 1%, and the lesson here being that we need to make improvements, not only in our ability to predict performance, but perhaps also to some of the design provisions. But this is the result of a numerical study. And as I have shared with the students in Professor Adams' group while I've been here, you perhaps have heard this at a conference. You have a theoretician talking, and nobody believes the theoretician except for the theoretician. And then you have the experimentalist come in. Everybody believes the experimentalist except for the experimentalist. Okay? So my point is, you need numerical results, and you also need experimentation. So in the United States, there was a program from 2004 to 2014 called NEES, the Network for Earthquake Engineering Simulation, where millions of dollars were poured into research to do experimentation. And many of those projects had to do with collapse. I was involved with one of them. And in this particular project, we actually conducted what is called hybrid simulation with substructuring. Let me explain what that means. Let's say we have a frame, a structure that we model as a frame. We have the two extremes. We can either model it in a computer and do a lot of numerical runs and feel very good about ourselves because our programs run and we get very neat results. Okay? Or we can take that structure, we can build it on a shake table. In Japan, you have the E-Defense table where you could build 9, 10-story structures, full size. At the University of California, San Diego, you also have an outdoor shake table where people have put 5-story buildings to shake. But you only have one chance. That's the problem. In the automotive industry, the aerospace industry, there are a lot of big challenges that are faced. No question about it. But if you're testing the wing of an airplane and a finite element model, you could take that wing and you could build a few of them and test them and calibrate your model. Buildings are a little bit different than bridges because each one of them is really unique. We don't just go in a factory and produce 10 buildings that are identical, especially multi-story structures. Okay? So we cannot afford to test all possible buildings or classes of buildings on a shake table. It's very expensive. And we could have safety concerns because we have to put big masses on the table. So a compromise is to do hybrid simulation, which is really nothing new because the Japanese have been doing hybrid simulation since the early 70s. But in hybrid simulation, what you do is you have a section of the structure that you model in the computer. And the rest of that structure you actually build in the lab. The advantage is you could build it at a smaller scale. You don't have to deal with the huge masses that you have to put on a shake table. Okay? So in terms of safety, it's better, it's more economical too than building the whole structure. And you have more freedom to try different design and different options. And the way this works is you start solving for the behavior of the structure in the computer. And there are displacements that are recorded at the intersection between the numerical model and the physical substructure. Those displacements are sent to the substructure. And then you apply the displacement with this actuator, these big jacks. You go to the displacement that the numerical model tells you have to go to. And then you record forces from the experimental substructure, and you feed the forces back to the numerical model. So you keep doing this back and forth until the end of the ground motion. But one question is, because we rely on numerical models also too, is how good are our numerical models? Because that portion of the structure that we model in a computer, we don't change during the analysis. We think we know how that portion of the structure is going to behave, and then we come up with models, simple or fancy models, and we just trust the models are doing what they're supposed to do, and we focus on the physical substructure. But now another question is, how good is hybrid simulation through collapse? Because until recent years, people started actually validating this approach all the way through collapse. I told you it has been around since the early 70s, but validation through collapse are minimal because of a lot of issues with instrumentation, experimental setup, and so on. But we were lucky, or fortunate, I should say, to have results from a shake table study where that frame was actually built by Professor Lignos and the late Professor Krawinkler on a shake table at the University of Buffalo, and it was tested all the way to collapse. So now we have a benchmark where we could take that same frame and we could do hybrid simulation with substructuring to validate this behavior to collapse. And that's exactly what we did as the first part of that project. My collaborators on the project were Professor Eduardo Miranda from Stanford and Professor Gilberto Mosqueda from the University of California, San Diego. This part of the project was led by Professor Mosqueda, where he actually, this is the bottom part of the structure that was built in the lab. The top was part of a numerical model, and we were able to trace through time the behavior of the structure all the way to collapse, using as a benchmark the behavior of the structure, the complete structure on the shake table. So that was a success for this particular building or this particular frame. But there were a lot of issues that we found. So with one of my students, one of the things that we developed, my student Miguel Negrete, and he is close to finishing his PhD. Hopefully he'll finish early next year. What we're doing, or what we developed, is a hybrid simulation framework that does the following. We don't assume that we know how to model these portions of the structure in a computer. We start with our best estimate of the numerical models. And then during the test, as we test the physical substructure, we not only send forces back to the numerical model, but the behavior of the structure during the test, we use to update the properties of the numerical model. So here, the underlying assumption is that the experimental substructure can tell us something about the rest. What we're testing can tell us something about the rest of the structure, which is a big assumption, but in a 4-story frame, steel frame, is not a bad assumption, actually. And we're actually to do this updating. And what I'm showing here is a plot that in the horizontal axis gives you time. On the vertical is some measure of deformation in the structure. So let's think about it. If you see in this plot at a given time that the deformation increases without bounds, that numerically implies that the building is actually falling. So you're approaching imminent collapse. Okay? Now, in the red line, we have a hybrid simulation where we purposely incorporate some error on the numerical portion of the structure. And with that error, the system didn't collapse. It displaced, but it didn't collapse. You don't see a high increase in displacement at time. Okay? Now, the black line gives you the actual behavior from the shake table experiment. And then when we implemented our updating approach, we started with the red model, but we're updating the properties of the numerical model based on what we learned about the physical substructure. We're able to trace and actually capture collapse at around the same time. Now, this is not the only result I have, but you see, people at conferences and in talks, they tend to present, I don't know if everybody knows it, but I have seen it, they tend to present their best results. I have results that are much closer to the black line. And I actually took this plot randomly. I just took one because I have confidence that in many tries, we're able to predict collapse and do much better than the red line. Okay? And why this is important? Because we want to improve our ability to predict collapse. I've also conducted hybrid simulation where we have the 20-story structure that I talked to you earlier, and we take a portion, a column in this case, and we test it in the lab. So we do hybrid simulation with a numerical model of the rest of the structure and this particular component there. Why? Because a lot of the testing that you see for calibration of components has to do with an element where you applied some loads, but those loads may not be representative of an earthquake. And what we can learn from this type of results is we have the column in there, and the demands at the top of the column corresponds to the demand that the whole structure is experiencing during an earthquake event. And well, this is just a picture of the setup. I'm just going to go over that quickly. And The bottom line with this particular set of experiments is we did the best we could to have a numerical model of this 20-story structure and expose it to an earthquake. When we did the hybrid test, the response of our column differed from the response of our numerical model. So after that, we updated the numerical model so that it actually matched. The numerical model is actually the magenta line, that it actually matched somewhat closely the experiment. So the models that we have, even with the best knowledge available right now, may not be enough or may not work well just to predict collapse numerically. So we need experimentation. We need both hand in hand. Okay? So I promise you I only have, I think, 3 more slides or something like that. So I'm almost done. Just bear with me for a few more minutes. Now, going back to our main goal, which is to protect lives and the built environment. Current building codes in the United States, for most structure, we talked about the 1% probability of collapse in 50 years, or if we have a design ground motion or an MCER ground motion, I should say, hit the side, we want a 10% probability of collapse. Obviously, this performance target change if you have a more critical facility, an emergency response center. The probability of collapse under the MCER ground motion is not 10%, but it's 3%. This is already incorporated in building codes. But we see there's a lot of uncertainty on predicting collapse. We can do better. We should do better. We need more experimentation to complement. And where we're headed is towards this. And I really want to stress this point. By 2022 or 2022, there are already talks that on that cycle, we may modify the load standard in the ASCE 7 committee to incorporate performance targets not only related to life safety, but also functionality and economic losses. Let's take these 2 examples here. If you have a building on risk category 3, okay, which could be a hospital where that doesn't have an emergency room of a certain size or a small one, and operating rooms that are limited to a certain size, they go into risk category 3, we may be designing such that there is a 40% probability, a maximum of 40% probability that under the 50-year life of the facility, the loss ratio doesn't exceed 10%. And the loss ratio is nothing more than repair costs normalized by total replacement costs. So think about it. I mean, for this to become a reality, we need research, and then we need proper communication with the general public, because what we're saying is, look, I can design this facility as an engineer, and then I'm somewhat confident that there is just this 40% chance that your loss ratio will not exceed 10% in 50 years. And then when you look at functionality, let's take that example. I talked earlier about the green tagging, yellow tagging, red tagging concept. When it comes to functionality, we may be designing, these are just examples, to have a 5% probability that under a 50-year period, your building will be yellow tag or red tag. At Christchurch, 45% of the buildings in the central business district were yellow tag and red tag. So this is a lofty goal, but there are a lot of researchers and practitioners actually communicating with research and working toward this goal. I am going to skip this one. And then talked about what is the new trend, not only in the United States, but over the world. The new focus right now, even though we're not there yet when it comes to earthquake engineering, the new focus is on disasters. Now there is a paradigm shift. We're changing from hazard mitigation to disaster mitigation, building disaster-resilient communities. These are communities that in the face of a hazard or a combination of hazards, the community can take a punch and recover, bounce back relatively quickly. If you have a bridge failing during an earthquake, that interrupts the network, the traffic network. What are the consequences of that? How do we control hazards from becoming major disasters. The National Science Foundation is actually putting a lot of emphasis on this specific topic right now in the US. And anyhow, just to wrap it up, just coming full circle to the words of Professor Helmut Krauwinkler, that still applies today. We actually want to deliver engineering facilities that respond to the diverse needs and objectives of owners, users, and society. Okay? And this is why research is very important. Communicating with practice, equally as important, and then communicating with the general public, perhaps, or at least equally important. I was going to say more important, at least equally important. And I just decided to put a picture of Professor Krauwinkler here because, as Sir Isaac Newton said centuries ago, and I'm going to paraphrase, if I can see further, it is because I stand upon the shoulders of giants. He was one of the visionaries, approximately 20 years ago, starting this performance-based engineering concept in the US. One of a handful of visionaries who had this idea of performance-based engineering, set up the stage and the principles to develop this framework that now as researchers were following right now. And I wanted to dedicate this talk to his memory. So with that, I'll open the floor for questions, and thank you for the opportunity to be here as a guest professor. And I cherish very much the opportunity to communicate with you or share with you some of my thoughts and my ideas regarding earthquake engineering and protecting lives and the built environment. Thank you.